All right, these are the video notes for lesson 1.4, and what we're going to do today is discuss graphing sequences. The basic idea is to explore graphing a little bit and how it ties into the terms in a sequence, and then look at also how we can classify what we're looking at based on the graph, and then connect up the idea of the graph to a very certain kind of sequence, and then do a little bit of modeling, which means check out a word problem that'll go with it. So let's go ahead and get started and just get the basics down. So how does a set of coordinates in a set of sequence terms connect to each other? And it's really a pretty simple idea. So if I'm looking at my coordinates and I'm trying to relate this to a sequence, what the x values actually represent is the term's position in the sequence. So if it's the 0 term, then that's going to be my y-intercept, for example. If it's the first term is 0, second term is 2, third term is 4, fourth term is 6, fifth term is 8, and so on. So if we look at a list of terms and we say the first term is 0, we can translate that directly to a coordinate saying the first term is 0. The second term is 2, the second term is 2. The third term is 4, the third term is 4. So the x values, when you guys think of a coordinate as x and y, the x values are the term's position in the sequence. The y value is its actual value. Graphing is very simple, so I'm going to lay these out quick and say, here we go, there's our sequence based on what we see up there as coordinates. Let's pop up some coordinates and check them out. And then things we want to start looking at is, can you identify what type of sequence we have? So if you look at the values going down the list, it looks to me like we're adding 2, adding 2, adding 2, adding 2. So right away my brain says it's got to be arithmetic, and I got a common difference of 2. Also write the recursive formula. Well, if I'm going to write the recursive formula and I'm adding 2, then my recursive formula goes use of n equals use of n minus 1 previous term plus 2. So in other words, I can generate this list by taking the number that came before it and adding 2 to it. So we can now take a set of coordinates that models an arithmetic sequence and say there's some things that we can actually match up with the idea of a line. First of all, does it look like it's a line to you guys? Well, not this line here. I'm going to get it sloping to fit, but I'm going to go ahead and overlay that. It looks to me like this definitely would form a line. From a geometry concept perspective, I should say, what is the D the same as? Well, if you start counting that from point to point and you go from left to right across the page, you're going to go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and so on. So what that really means is now D, a common difference in an arithmetic sequence, can also be considered to be the same concept as slope when we look at the graph. And also it's true that our use of 0 term would be our y-intercept. Because again, a 0 comma any number is an automatic y-intercept. So what we're trying to do here is connect now an arithmetic sequence to the concept of a linear graph, which actually turns out it always will be. So arithmetic sequences are always linear all the time. And D, the common difference, can now be considered to be the same concept as slope, and use of 0, our initial term, our starter term, can now be considered to be the same thing as the y-intercept. So there's a good connection to make right up front. We're going to go through just a couple more slides and just kind of pinpoint, kind of narrow things down a little bit, keep these connections going, and also talk about geometric so we can compare the difference. Now let's just start with this. Before getting to geometric, let's say you didn't really know much about any of the graphs, how they connect to a recursive formula, but you at least know a couple things about graphing. So one thing I would do in these problems, we're going to try to take all 6 graphs and then we're going to drag them in here and match them up. So right now they're not sitting in any particular correct spot. But I'm going to drag them in and match them up, and what I want to do is all these spots that I kind of have in blue and red here are y-intercepts. And now knowing from the previous slide that the use of 0 is the y-intercept, then what I'm going to do is I'm going to write down all of my y-intercepts just real quick. So, and some of them are the same, so that's only going to help us to some extent. And then what I'm going to do is start going through my graphs and look at those graphs that are linear and try to match D to the slope. That'll at least get my arithmetic sequence there, or my linear graphs matched up, and then I can go back and work on the rest. So for example, the first one, I've got a y-intercept of 8 and a slope of -2. So if I scan through my graphs, my y-intercept of 8 is here. I've also got one here, but that's a curve, not a line, right? So a slope of down 2 over 1, down 2 over 1, down 2 over 1. Looks like that's definitely my match. When I go to look at the next one, don't really see the idea of arithmetic going on. I'm going to pass that one by, pass that one by. Here's arithmetic. So we got a slope of -2 and a y-intercept of -2, and the d common difference is the slope of 2. So start at -2 and up 2 over 1, up 2 over 1, up 2 over 1, which is that graph. So we're going to do a little bit of just pulling things out here and switching them around. Then as I scan through, I see one other one that looks to me like it could be arithmetic. I've got a y-intercept of -4. I see one more graph that's linear, which is this one. And let's just see if we can figure out how it is that it fits that rule. Now what this rule says is that every term is the same as the previous term, so u sub n equals the previous term. So in other words, there isn't like doing a just subtraction. The idea is you're actually always going to get 4. So every term in the sequence is 4. As a graph, what that means is the zero term, -4. The zero term is -4, the first term is -4, the second term is -4, the third term is -4, and so on. So it turns out this is linear, it's a horizontal line. So I've taken out those that I know are linear, those that are arithmetic, and now it leaves me with some curves. Okay, well, with curves, because we haven't discussed that just yet with geometric, but at least I can pick out y-intercepts. So a y-intercept of 8, a y-intercept of 0.5, and a y-intercept of -2. And basically I got them all squared away in the right spot. So what makes it geometric? Well, it looks to me like when I do geometric, I have a curve. Now, again, looking at these rules, formulas, how do I know they're geometric? Multiplication times the previous term, multiplied by the previous term, multiplied by the previous term with some addition, so that's shifted geometric, but it's still geometric because I'm multiplying. So from what I'm gaining from this slide, I got my linear, arithmetic, and it looks to me like geometric are curves. And I can rely on the y-intercept and the common difference as slope when it's linear. When it's a curve, geometric, I'm pretty much relying on my y-intercept. Okay, let's do one more individual graph. Actually, we'll do two. We'll look at the arithmetic and the geometric both, kind of one more comparison. So we're going to generate a table, in other words, generate a set of coordinates. We got a u sub 0 or a y-intercept of 0, 5, and there it is plotted. Our rule says add 4 to the previous term, so we're going to start adding 4 and plotting. So 5 plus 4 is 9, 9 plus 4 is 13, 13 plus 4 is 17, and my points match. Is it linear? Absolutely. But I knew that already from the previous discussion of arithmetic is linear, right? And so my d is 4, my u sub 0 is 5. Remember, this is actually a slope. And I can say now circle the things that I know are true. So where it's arithmetic, it's linear. So I'm going to take those out. Increasing or decreasing is easy enough. Just track your values as you go left to right. So as I go left to right, clearly we're increasing. Or left to right as I read my graph, that's an increasing idea. So we can say it's increasing. So some categories to kind of fit things into. And again, the big connection here is that we want to consider all arithmetic sequences to be linear. You don't really need necessarily draw a line so much, but it's a matter of what the points represent. They model a line. Okay, let's do a geometric, and then we'll throw a word problem in, and we'll wrap it up here in a few minutes. So multiplication, so I know it's geometric. We got our u sub 0, which is our y-intercept. That point's already been plotted. R is 1/4. Sitting right here, u sub 0, 16, so I got that information. Again, this is a y-intercept. This is not a slope, because remember, it's not linear when it's geometric. But let's run some terms here. So 16 times 1/4 would be 4. 4 times a fourth is 1. And 1/4 times a fourth is 1/4. Now, just to kind of prove it to you guys quick, if I tried to somehow get this line to fit, it does not fit at all, right? So I know it's not linear for sure. It's a curve. There's a curve moving down through here. And geometric is a curve. So we know it's geometric. We say nonlinear instead of saying a curve. And then the values as I run across here are clearly going down, decreasing, so it's decreasing. So I think the idea of connecting a graph to a sequence is pretty easy because they're really just going cut and dry, sort of two things, right? We got linear arithmetic, we got curve geometric, and that's all really we have to get out of it. Okay, let's get to one last one here and we'll wrap it up. So looking at kind of mixing a word problem into the whole idea. So an owner of a small apple farm, orchard, picks 800 Honeycrisp apples to sell in their apple shop for the fall apple season. Each day the orchard plans to sell 25% of its apples and pick 50 more. So this is that idea we talked about a few days ago with the tree farm, the nursery, right? So we're going to sell off so much, but we're going to go out and replenish our stock so we keep a certain amount always on hand. That's the idea. So make a graph that shows the number of apples available for sale over the next 10 days. And what we think with this process, what the orchard would want to have happen is that we can keep a certain amount in, so we sort of level off after a while, and we've got it right where we want it. So for starters, let's get a couple things in. We know our starter is 800. That was the original amount picked. 0.75. Now, why didn't I use 0.25? Because what the problem says, what we're trying to do is figure out how many apples are there, right? How many apples are in the shop, in stock. So 25% goes out, that's a P. 75% remains, that's an R. And then plus 50 is our shifted geometric, so we add that on. We'll now start generating terms, right? So we're going to go 0.75 times 800 plus 50. So 0.75 times 800 plus 50, and then 650 times 0.75 plus 50, and so on down the line. Remember, in my calculator, I probably am getting decimals, but I'm rounding to whole numbers because, again, we're talking about objects. And you can't have half an apple, you won't sell half an apple, put it that way, or point something of an apple. And we get to 232 in 10 days. So you can see 650, and all of a sudden we get to the back end here, and we're starting to go up at a very small increments, so we're starting to level off. And with our curve, geometric, right, we see our curve, we're going to see our curve start to level off. Now the idea is long run, so let's say the apple season in the fall, maybe a month, somewhere around there. So this is only 10 days in, and we want to just kind of see, like, if we keep this process going, what will we always have on hand? So long run value, remember what you do with that is you take your original formula and you replace the use of n terms with x's. And keep in mind that's a 1 out there, so I replace that with an x, that with an x. Do a little bit of basic algebra, subtract 0.75 to both sides, divide by 0.25, and I get 200. Long run. So if this goes out beyond 10 days, for 2 weeks, let's say, or 3 weeks, it looks like, and this is actually, we're talking about days out here, so here's about our 2 week mark, we're probably going to level off at about 200. And I always have that much on hand all the time. Okay, so again, long run is a projection. What do I think will happen over time if I keep the same process going? All right, and that wraps it up for the 1.4 notes on graphing sequences.